So in this video we're going to solve trigonometric equations by factoring and using the zero product property when the equation is in quadratic form. So for the first example it says in degrees, find all real roots of f of theta equals tan squared of theta minus 1. And we want to remember that when we're looking for roots, we are looking for those places that the function f of theta is equal to 0. And I want to recognize then that I would need to set tan squared of theta minus 1. Tan squared of theta minus 1. I would want to set it equal to 0. I also want to recognize that this is a quadratic form. This looks like a quadratic equation in the sense that if we make the substitution x equals tangent of theta, so we replace tan theta with x, we would get something that would look like x squared instead of tan squared minus 1 equals 0. And then we could ask the question, if I had a quadratic equation, what could I do to solve this? So there's a couple good methods for this particular one. One would just be to simply add 1 to both sides and then take the square root of both sides to cancel the squaring on the x, recognizing that when we take the square root of both sides we have to put plus or minus. So we would get x equal plus or minus 1 and we would be done. So I could take the same approach to this trigonometric equation that's in a quadratic form by making the same algebraic moves I would make with a quadratic equation. So here I'm going to add 1 to both sides, and that's going to give me tan squared of theta equals 1. I'm going to take the square root of both sides to cancel the squaring, and that's going to give me the tangent of theta equals plus or minus 1. But whereas with the quadratic equation I was done, here I'm not done because I know what the tangent of theta is, but I don't know what theta is, and that's what we need to know. We need to know what values of theta will give us a value of 0 right here for our output. So we have to keep going. We're going to take this and break it into two equations at this point. We're going to say, hey, the tangent, either the tangent of theta equals positive 1 or the tangent of theta needs to equal negative 1. So solving this one, we take the inverse tangent of both sides. Theta equals the tangent inverse of 1. We know that the tangent function has a period of pi radians, so solutions repeat themselves every pi radians. So we want to add on plus pi k, where k has to be an integer. And then we want to check, is the side ratio 1 a special, does that correspond to a special angle on the unit circle? So when I peek at the unit circle, I want to remember that the tangent inverse function, I don't want to do pi k here. I'm being bad because we want, this example, we want the answer in degrees. So instead of saying that the period of the tangent function is pi radians, we're going to say the period of the tangent function is 180 degrees. So it's going to be this angle plus 180 degrees times k, where k is any integer. The solutions repeat themselves every 180 degrees. And then we go to the unit circle. We say on the unit circle, the tangent inverse only gives us outputs between negative 90 degrees and 90 degrees. So is there a place on the unit circle where the side ratio is equal to 1? And there is, because at the 45 degree angle mark, we have the ordered pair root 2 over 2 comma root 2 over 2. And we remember that the tangent function is defined to be the ratio y over x. So in this case, because y and x are the same value, y over x will be equal to 1. So we go one more step. We recognize we can simplify this because it corresponds to a special angle. So we replace tan inverse of 1 with 45 degrees, and it's going to be plus 180 degrees times any integer k. Now we step over and solve this other equation that we got. So we're going to take the tangent inverse of both sides again. So we get theta equals the tangent inverse of -1. We want to recognize that the period of the tangent function's pi radians are 180 degrees, so the solutions repeat themselves every integer multiple of 180 degrees. Then we want to look at the side ratio -1 right here and say, hey, does it correspond to a special angle? Does a special angle generate this side ratio? And it does, because -45 degrees corresponds to the ordered pair positive root 2 over 2 for the x-coordinate and negative root 2 over 2 for the y-coordinate. And when we take the ratio y divided by x, we'll get a -1. So we can substitute tan inverse of -1 with -45 degrees plus 180 degrees times k. And so kind of clearing this mess here out of my way, these are my two solutions, and I want to recognize I can probably write them in a very compact form. Theta equals, hey, 45 degrees or -45 degrees. That's just plus or minus 45 degrees plus, they're both plus 180 degrees times k. So this would probably be the most efficient way to solve this one. However, just to point it out, if we were working with a quadratic equation that looked like this, another approach would have been to recognize that x squared minus 1 is the difference of two squares, which means it's factors easily. So we could rewrite this as x plus 1 times x minus 1 in factored form, and then use the zero product property, a times b equals 0, to say, hey, x plus 1 equals 0, or x minus 1 equals 0. So we could have done the same thing with the tangent function up here. We could have recognized that this could generate the tangent of theta plus 1 times the tangent of theta minus 1 in factored form equal to 0. And we could have used the zero product property to solve this as well by factoring. So the next example, it says find in degrees all solutions to this equation, cosine squared theta minus cosine theta minus 2 equals 0. So we'll rewrite the equation. We have cosine squared theta minus cosine theta minus 2 equals 0. And I want to recognize that this is also in a quadratic form. If we let x represent the cosine of theta, so we make the substitution. Everywhere we see cosine theta, replace it with an x. What we would get is x squared right here minus x minus 2 equals 0. And then we could think back to our algebra classes, and we could say, what are the techniques we know to solve this? Hey, we can factor and use the zero product property. We can use the quadratic formula. We can complete the square. There's all kinds of things that we can try to do. So in this one, we can try to factor it. So if it factors nicely, it's going to be x times x, or if it factors easily, it's going to be x times x. And then it's going to be, I have a minus 1 here, so probably minus 2 plus 1. And then you could multiply to check your work. X times x is x squared. Minus 2x plus 1 times x is minus x. Minus 2 times 1 is minus 2, so that checks. And then you would say, hey, I can use the zero product property. I have a times b equals 0, so either x minus 2 equals 0 or x plus 1 equals 0, and then we could continue to solution. So we're going to look at this and say that you are in a quadratic form, and you're going to factor like this, except instead of x's, it's going to be cosines of theta. So I'm going to get cosine theta times cosine theta to get cosine squared of theta, just like I get x times x is x squared. And it's going to be minus 2 plus 1. And now I recognize that I can use the zero product property because I have a times b equaling 0. So either a equals 0 or b equals 0. So we're going to create two equations. We're going to say, hey, the cosine of theta minus 2 equals 0, or the cosine of theta plus 1 needs to equal 0. And then if we start trying to solve this, like if we were working this, we would add 2 to both sides, and then we would be done. So here, same strategy, isolate the cosine function. We get cosine of theta equals 2, and here you want to stop. Why? Well, the cosine of theta, the range, only gives outputs between -1 and 1 on the unit circle, and 2 is not in the range of the cosine function. 2 is not an element of the interval from -1 to 1. The cosine function, when it's zipping along, has a high of 1 and a low of -1, and that's all it ever gets. It doesn't get up to 2 unless you do some sort of vertical translation. So this, so the cosine, when does the cosine of theta equal 2? Never. So this one has this equation here, there's no solution sitting there. So we stop. So we step over here and say, well, will this have a solution? Well, we subtract 1 from both sides to get the cosine function by itself. -1 is in the range of the cosine function, so I'm going to go ahead and take the cosine inverse of both sides. So I'm going to take the cosine inverse of -1. I want to get all coterminal angles, so I'm going to add on plus, and we want it in degrees, so it's going to be plus 360 degrees times k to get all coterminal angles. And we remember that the cosine function has even symmetry. Looks like this. And whatever angle we get here, generating an output, we get the opposite of that angle, so we get plus or minus the cosine inverse. And right now there's a sense in which I'm done. I've got all solutions, but I do want to look at this and say, hey, can I simplify this here? Does -1 correspond to a side ratio or an x coordinate on the unit circle that is associated with a special angle? And we know that the cosine inverse function is only defined from 0 to 180 degrees. And at 180 degrees, we have the ordered pair -1, 0. And the cosine of theta is the x-coordinate on the unit circle. So 180 degrees is the angle that generates a side ratio of -1. So we replace cosine inverse of -1 with its simplified form, 180 degrees plus 360 degrees times k. And then I can go a little bit further than this because I want to recognize that 180 degrees, which is a half counterclockwise rotation, and -180 degrees, which is a 1/2 clockwise rotation, they are coterminal angles. 180 degrees is equivalent to -180 degrees in the sense that they're coterminal. So I actually don't need to go 180 degrees plus 360k to get all coterminal angles. If -180 is a coterminal angle, then 180 degrees plus 360k gets it. So I actually, in this case, is a special case where I don't need the plus or minus. And so here I have all solutions as long as I tell the reader that k needs to be an integer 0 plus or minus 1 plus or minus 2 and so on and so forth. And we have one more example if you're interested in seeing it. So one more example with a quadratic form. So it says find all solutions in radians this time to the equation cotangent of theta times cotan theta plus 3 equals 1. So I'm going to rewrite the problem. So this is one where if I subtract 1 from both sides so that I get a 0 on the right hand side, and I have a subtract 1 sitting here, subtract 1 from both sides, and then distribute the cotangent in, I get cotangent squared of theta plus cotangent of theta times 3 gives me plus 3 cotangent of theta minus 1 equals 0. This, if I let x equal the cotangent of theta, I have a quadratic form. X squared plus 3x minus 1 equals 0. This equation has this quadratic form. And if I have this, I could say, maybe I'll try to factor it and put it into factor it so I can use the zero product property. So if I were going to factor, I get x times x. And then you have to ask the question, if it factors nicely, what are the nice ways of making negative 1 using a product? Well, there's only one way to do it, minus 1 times plus 1. But if we multiply this out, this is a difference of two squares. You wind up getting x squared minus 1 equals 0, which isn't this. So this is one where it's not going to factor easily or nicely, if you want to think of it that way. So if we have something that doesn't factor nicely, what are our big tools for solving it? Well, we either complete the square, which is my favorite way of doing it, complete the square, or use the quadratic formula. And this is probably most people's preferred method if they have something like this. So if we were to use the quadratic formula instead of completing the square, what would we get? We would say, hey, what's the quadratic formula? It's x equals what? The opposite of b plus or minus square root b squared minus 4ac all over 2 times a. And in this case, a would equal 1 because 1 is the coefficient on x squared. B would equal 3, the coefficient on x. And c would equal the constant term, which is a negative 1. And we would plug it into this quadratic formula and go. So we can do the same thing over here, except it's not going to be x equals. Instead of x equals, it's going to be cotangent of theta equals. So we're going to get cotangent theta equals opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. A equal 1, b equal 3, c equal negative 1. That's not going to change. The coefficients are the same. So we plug those in. We get cotangent theta equals the opposite of b, which is going to be, the opposite of 3 is going to be negative 3, plus or minus the square root, and it's going to be 3 squared, minus 4 times a is 1, times c is negative 1, all over 2 times a. And then we just simplify. We get negative 3 plus or minus. We get 3 squared. We have a minus and a minus, which is going to give us a plusy. So we're going to get 9 plus 4 times 1 times 1 is 4. 9 plus 4 is 13. So we'll get negative 3 plus or minus the square root of 13 all over 2. And this is what the cotangent of theta needs to equal. If this were an x equal, we would be done. But this actually is giving us two separate equations that need to be solved now. So we either have to solve the cotangent of theta equaling negative 3 plus that square root of 13 all over 2. There's one equation. And the second equation that we would need to solve is negative 3 minus. So we would get cotangent, hope we have enough room here, cotangent of theta equaling negative 3 minus the square root of 13 all over 2. So to get theta out of here, we would take the inverse cotangent of both sides. So we get theta is the cotangent inverse of negative 3 plus the square root of 13 all over 2. And we want to recognize that the period of the cotangent function's pi radians, so answers repeat every pi radians. So we're going to go plus pi times k, where k is any integer. And here we're done. This is it. This doesn't correspond to a special angle. We're done. If we needed to get approximations by plugging this stuff into a calculator, not all calculators have an inverse cotangent function on them. So what we would need to do is use the tangent inverse instead. So what we want to recognize is that the cotangent and tangent are reciprocals. So the cotangent inverse of this ratio, this side ratio, is the same as the tangent inverse of the reciprocal of this side ratio. So tangent inverse of 2 over negative 3 plus the square root of 13, and we'd be plus pi k, and then we could get decimal approximations out of the calculator if we needed to. So if we step over to solve this one, if we might even here say, hey, I'm going to need to use my calculator at some point to get decimal approximations. I could just recognize that the cotangent is the reciprocal of the tangent. So the tangent, if the cotangent is this, the tangent is the reciprocal of that. So we just flip everything over. And then take the tangent inverse of both sides. Tangent inverse of both sides. So we get tangent inverse of 2 over negative 3 minus the square root of 13. And then the tangent function has a period of pi radians, just like the cotangent function does. So this is one angle, but we want all angles, so we're going to go plus pi times k, where k is any integer. So here's the other solution. So if we want to put it all together, we could say, hey, either theta is going to equal the tangent inverse of 2 over negative 3. Ooh, could we just go plus or minus right here and get it? Negative 3 plus, we could probably just put plus or minus right here and call it a wrap. I'm not going to do it, but that would sure be a fabulous way to write that, plus pi k. Or we could do the tangent inverse of 2 over negative 3 minus the square root of 13. And yes, the more I look at this, the more I just wanted to write it plus or minus the square root of 13. I think that would be a fine way to do it. And we need to tell the readers that k needs to be an integer.